Hello, today we're going to talk about capacitors. So we have three goals today. We'll talk about capacitors, that'll be one. And what is a capacitor? Well, in general, it's a device that can store electric charge. Our second goal, we'll talk about the energy that's stored in a capacitor. We'll go over some equations for the energy. And finally, we'll talk about what happens when a piece of insulating material, we normally call that a dielectric, is placed in between the capacitor plates. Okay? There are certain advantages to doing that, so we'll talk about those. Okay, and we're going to focus on what's called a parallel plate capacitor. And it's very easy to draw a parallel plate capacitor. You imagine on a piece of paper you just draw one line, another parallel line next to it, and they're just separated by some distance. Okay, and in real life you could make one out of two cookie sheets. You could have one cookie sheet directly facing another cookie sheet, parallel to each other, some space between them. If you hook those two cookie sheets to a battery, the battery would pump charge from one plate to the other, from one cookie sheet to the other, and you would have a parallel plate capacitor. Okay, so again, what is it? It's a pair of identical conducting plates. They each have area A. They're parallel to each other, separated by some distance d. So we define something we call the capacitance. Well, here it is. And one thing it is dependent on the geometry of the capacitor itself. Okay? So here are the capacitance. We're using our symbol C for capacitance, is some constant epsilon naught, that's this funny squiggly E with a 0 next to it. You say that as epsilon naught, N-A-U-G-H-T, naught, times area, A, divided by D, the distance between the plates. What is capacitance? Well, it's a measure of how much charge the capacitor can store for a given potential difference between the plates. Okay, so with a certain let's say your cookie sheets are connected to a 3-volt battery. Okay, you'll get a certain amount of charge pumped by the battery from one cookie sheet to the other. So one plate will have positive Q, the other plate will have negative Q. We say the capacitor stores a charge Q in that case, even though the magnitude of the charge on each plate is Q. Okay, so really it's pumped minus Q worth of electrons from the positive plate over to the negative plate. So there really is an amount Q of charge that has been transferred from one plate to the other. Okay, so if we instead hook up our cookie sheets to a 6-volt battery instead of a 3-volt battery, we're going to get twice the charge on it. I'm kind of getting ahead of myself, but we'll get to that in a second. That equation will come at the end of the screen, I think. Okay, this thing epsilon naught is called the permittivity of free space. It's got a very, very fancy name, permittivity of free space. But don't worry about that fancy name. It's just simply this value, and it's connected to K, our constant that's in Coulomb's law, K QQ over R squared. And so you could, if you want to, write this capacitance equation in terms of K. You could write it as A over 4 pi K times D, if you wanted to. That'd be fine. Anyway, 1 over 4 pi K happens to be 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. So that's our epsilon naught value. And then here's the equation that I was alluding to earlier. The charge on the capacitor plate is the capacitance multiplied by the potential difference, the voltage across the capacitor itself. Okay, but remember the capacitance is determined by these geometric factors, the area of the plate, the distance between the plate, and this constant, epsilon naught. And we'll see in a few minutes that it's also determined by what we have in between the plates, but we're not going to get to that quite yet. Okay, so there are generally two cases in which we use a capacitor. So here we have a picture of a capacitor, and one plate is colored red and the other plate is colored blue. And the red one is the positive plate. And why is it positive? Well, it's because when you trace the wire connected to the red plate back up, you see it's connected to one side of the battery. The battery is drawn very much like a capacitor is drawn in a circuit. It's got two parallel lines on it, the battery symbol, but one line is shorter than the other one. The long line on the battery is the positive terminal. The short line is the negative terminal. Okay, so the positive terminal of the battery is connected to one plate of the capacitor. Remember, these capacitor plates can be simply cookie sheets, and that makes that plate positive. The negative terminal of the battery is connected to the negative plate of the capacitor. It's negative because it's connected to the negative terminal. Okay, so originally these two plates were neutral. When you connect them to the battery with the two wires, what happens is electrons get pumped from the plate that ends up positive. This is why it ends up positive, because the electrons leave there. They're pumped around through the battery, through the other wire, to the other plate. And that's why that plate ends up negative. Okay, and if you have a 6-volt battery, then you'll end up with 6 volts across the capacitor. In this case, where that's all there is in the circuit. Just a capacitor, 2 wires, and a battery. Okay, so this is one regime where we use the capacitor. The battery will always be connected to the capacitor plates. And so then you can change some things about the capacitor. You can put things between the plates. You can change the spacing between the plates, for instance. Maybe you can figure out some way to change the plate area. Okay, so when you do that, because it's always hooked up to the battery, the capacitor voltage will always be equal to the battery voltage at all times. Okay, so as you play around with the spacing and things like that, the charge on the plates will change, but the voltage is fixed. And the charge changes because you're changing the capacitance of the capacitor by varying some things. So let's see this in action, okay? And then we'll talk about a second case, a second regime in which we use a capacitor. But there's really only these two regimes. The first one we're doing is when the battery is connected. The second one, of course, is when we charge the capacitor and then disconnect the battery. So we'll do that in a few minutes. Okay, so let's see a little animation of the capacitor when the battery remains connected. Okay? And so what we're going to do is we have some sliders here. We can change the distance between the plates, so we'll certainly do that. And you can see at the bottom there's something in green, which is the capacitance in terms of the initial capacitance. In light blue is capacitor voltage. That's always going to stay fixed in this particular animation because the capacitor is always connected to the battery. The red thing is the amount of charge that's stored on the capacitor. The purple to the right under the blue is the electric field, and it's kind of another purple, which represents the amount of stored energy in the capacitor. Okay, so the capacitor stores charge, and because of that, it stores energy, electrical energy. Okay, so we're going to see what happens as we first vary the distance between the plates. So let's try that, and then we'll actually put a piece of insulating material in between the capacitor plates and see what happens there. And that'll be with the dielectric constant slider. When there's air between the plates, air has a dielectric of 1, a dielectric constant of 1. Okay, so that really doesn't change anything about the capacitance. But when you insert a piece of dielectric, you can actually change the capacitance, and we'll get to that before we're done this movie here. Okay, so here we go. We're going to start by changing the distance between the plates. We'll start by decreasing it. And what happens there is as you decrease it, well then the positive charge and the negative charge on the plates are closer to one another, and so it's easier actually for the battery to store more charge in that case. As you push the plates farther and farther apart, what happens is all the electrons on the negative plate really now just see one another, and they want to run back to the positive plate on the other side through the battery. So the battery actually cannot store as much charge when the plates are far apart as it can when the plates are close together. Okay, so now we're introducing a piece of dielectric, and we're actually modifying the dielectric constants. We're sort of trying out all sorts of different insulating materials with different dielectric constants. And you're changing the capacitance, change the charge, change the energy. It doesn't change the voltage at all because the capacitor voltage is matching the battery voltage at all times because the capacitor is still connected to the battery. And in this case, we're no longer changing distance, and if you're no longer changing distance, then your field doesn't change either. Okay, so I'll talk some more about this dielectric business later on. Okay, but as you change the distance or the dielectric constant, you can see charge changes, energy changes, field will change if you change distance, capacitance is changing. The one thing that doesn't change is the voltage in this case. Okay, now we'll do case 2. So case 2, this is what happened. We had the capacitor hooked up to the battery. The battery pumped electrons from the left plate through the right plate, and it did that by taking the electrons off the plate on the left, sending them through the wire, through the battery, through the other wire to the negative plate. That's why that plate ended up negative. Okay, so now we've done that. Now we open a switch in the circuit, and we just need to open a switch on one side. And then these electrons on the right-hand plate of our capacitor cannot get back to the positive plate anymore. Okay, so they're stuck on the capacitor. So with the battery disconnected, what happens is the charge is constant on your capacitor now. Okay, so this is kind of the second regime in which you operate the capacitor. You charge it, and then you disconnect it from the battery, so the charge is constant. And then again, you can play with some things. So we'll see what happens now when we play with the, so first we'll open the switch, disconnecting the battery from the capacitor. And so now different things happen than what we saw before. Here we got the charge is constant, the voltage now is changing, interestingly enough. You can even make the voltage more than you got from the battery by making appropriate changes in the capacitance. Okay? Well, that's interesting all by itself. Okay, now the charge sets up the electric field, so you note the field is not changing until you change the dielectric constant. And we'll talk about why that is later on. Okay? So here now the voltage is changing. The charge, no matter what we're doing in this case, stays the same. So the energy is changing, capacitance is changing. Okay, and we'll talk about why these things have the particular values they have. Okay, but always think about whether the capacitor is connected to a battery or disconnected from the battery when you're considering questions about what happens when you change this or that. Okay, either the capacitor voltage stays constant if the battery is still connected, or the charge stays constant if the battery is not connected. Okay, so let's talk about field. We saw some things going on with the field in our animations there. And one thing we do is we assume that the electric field between our parallel plate, inside our parallel plate capacitors, is a uniform field. Okay, as long as our plates are pretty big compared to the spacing between them, that's actually not a bad approximation. Okay, so field points across the gap of the capacitor plate from the positive plate to the negative plate. Okay, we say our potential difference across the capacitor is delta V, the distance between the plates is D, then our field is simply delta V over D. That's just magnitude-wise. Okay, the direction again is from the positive to the negative plate. Okay, so there's electric field in a capacitor. And really that stored energy is stored in this field. Okay, so let's talk about energy some. Now, what's going on with the capacitor is the battery is causing electrons to move from one plate to the other. If you take a single charge and move it through a potential difference, its potential energy changes by an amount equal to the charge times the potential difference. And we're moving a whole bunch of charges from one plate to the other. We're moving a bunch of electrons from the positive plate, the plate that ends up positive because we're causing electrons to leave that plate, over to the negative plate. And that plate again ends up negative because electrons are arriving on it from the other plate. They're being pumped over there by the battery. Okay, now it turns out if delta V is the final potential difference on the capacitor, Q is the magnitude of the charge on each plate in the end, then the energy stored is not Q delta V, but 1/2 of Q delta V. And that's because, on average, the charge is removed through a potential difference of 1/2 of delta V. So you imagine you start with completely uncharged plates. Okay, there's no potential difference at all between them in that case. You move the first electron over and moves over again with through no potential difference at all. Okay, and then you've got a very small imbalance in charge between the two plates. You have a very small potential difference. Then you move the next electron. That takes you some work because there's a certain small potential difference there, but not much. And you keep doing this. And the more electrons you move, the harder it gets because as you charge the plates, you get a bigger potential difference across them. And so it takes more work to move successive electrons over until finally an equilibrium is reached and you stop moving. You can't move anymore, actually. So you've reached the voltage on the capacitor. The voltage on the capacitor matches the battery voltage. That's when everything stops. Okay, so on average, the charge is moved through a potential difference of 1/2 of the final voltage. First one went through a potential difference of 0. The last one went through a potential difference of the full delta V. On average, they came through 1/2 a delta V worth of potential difference, so your energy in the end is 1/2 a delta V times Q. Okay, and using Q as C delta V, we can rewrite that energy equation in 3 equivalent forms. Here's 1/2 Q delta V. We can also write it as 1/2 C delta V squared, or Q squared over 2C, 1/2 of Q squared over C, in other words. Those are completely equivalent ways to write that energy equation. Okay, but basically, the more charge you store, the more energy you have in general. The more voltage you have, the more energy you have. Okay, so now finally we'll talk about dielectrics here. And a dielectric is a new word, but it's a word for something we've really talked about before, which is usually a piece of insulating material. Okay, so you take your capacitor plates, your 2 cookie sheets, and you put a bunch of paper in between the plates, or you put a styrofoam block in between the plates, some insulating material. And what happens is the insulating material is affected by the field in between the capacitor plates. Okay, so here's the first picture on the left represents a dielectric material, a piece of insulating material made up of polar molecules. Now those polar molecules are randomly arranged when there's no field that insulating material is exposed to. Now if you put this in the capacitor is charged, there's a field in between the capacitor plates pointing from the plus plate to the negative plate. That will tend to align these polar molecules. And what happens is the left face of your insulating material has a kind of a line of negative charge on it. The right face has a bunch of positive charge. In the middle, kind of you get negatives next to positives, and they kind of cancel each other out. But you get net charge at the face, at each face, the left and right faces, in fact, of your piece of insulating material. Okay, so let's look at this again. So the insulator is this kind of yellow thing, kind of beige thing maybe, and you stick it in this field created by the plates of the parallel plate capacitor. And then what happens is you get an induced field in the insulating material itself, in the dielectric, which points in the opposite direction to the field from the capacitor. And so you get a net field. The net field is always in the same direction as the original field, but it can be less. In one of the cases with our capacitor, what would happen is if you charge a capacitor, disconnect the capacitor from the battery, then put your insulator in, this set of pictures applies to that case. Your electric field in the dielectric material is less than you were getting from the plates to begin with. Okay? Okay, so, and I started with the original picture on the left as an insulating material made out of polar molecules. However, even if these were unpolar molecules, when they're in the field, you polarize those molecules. And so the same kind of thing happens with a bunch of negatives on one face and a bunch of positives on the other face. So you don't have to start with polar molecules. They can be nonpolar to start with. Okay, now, if your capacitor is connected to a battery, what happens is the capacitor then brings the field back to its original value. And how does it do that? Well, it stores more charge on the capacitor. So it actually is easier to store charge on the capacitor with the dielectric in it. And the whole goal of the capacitor is to store charge. So by making it easier to store charge, you've got a better device. Okay? Okay, so let's just go over what the dielectric constant represents. So every material has a particular dielectric constant, and really it tells you how effective the dielectric is. So you really want to increase the capacitance of your capacitor by the largest amount, so a big dielectric constant is good. Okay. So what happens is we say, okay, if you've got your capacitor disconnected from your battery, when you insert your dielectric in the capacitor plates, the field goes down in that dielectric. So you take the ratio of the original field, that's E naught, the field without the dielectric, to the ratio of the new field with the dielectric, and the new field is less, so that ratio is some number bigger than 1. It doesn't have any units, the units have canceled out, but some number bigger than 1. Unless you have vacuum or air in between the plates. Air is not quite the same as vacuum, but in this situation it's basically the same thing. So air and vacuum, we say, have dielectric constants of 1. Insulating materials generally have dielectric constants of more than 1, 3, 5, 75, something like that. Okay, depends what the material is. Okay, so then we get a new equation for our capacitance. We just modify the one we had before. So before we said capacitance is epsilon naught A over D. Now we say it's kappa. This is actually the Greek letter kappa. It looks a bit like a K. It's the Greek letter kappa, that's the dielectric constant, times epsilon naught A over D. So if the dielectric constant of the insulating material you place inside the capacitor, between the capacitor plates, is 5, you've just increased your capacitance by a factor of 5. You increase it by a factor of kappa, the dielectric constant. Okay, sound all right? So we did a lot of equations today. So let's just summarize really the key ones, okay? So here's our capacitance equation. Capacitance, again, is determined by what the capacitor, how you put that capacitor together. The area of the cookie sheets you use, the distance between the cookie sheets, the material you sandwich in between the cookie sheets, what the dielectric constant is, okay? Kappa epsilon naught A over D, and epsilon naught is just a constant. Okay, now why do you use capacitor? Remember, dielectric constant of air is 1. Okay. Why do you use a capacitor? Because you're trying to store charge. The amount of charge stored is the capacitance times the voltage. Okay, double the voltage, double the charge. And you want to try and make the capacitance C as large as possible to store as much charge as possible for the same voltage. Okay, then we've got electric field. Electric field between the plates is delta V over D. This is just magnitude. Again, that field we assume is uniform, and it points from the positive plate to the negative plate. And then we've got our energy equations and 3 equivalent forms of the energy equation. So the energy stored in the capacitor is 1/2 Q delta V, or 1/2 C delta V squared, or Q squared over 2C. Okay, so with all of those, you can do all kinds of fun things with capacitors. Charge them, disconnect the battery, change the plate spacing, see what happens to field, energy, charge stored, etc., etc. Potential difference, things like that. Okay, so that's the kind of things we'll be evaluating, examining when we get to class.